Hello everyone, my name is Kun-Ting Chen. Today I'm going to present our paper. It's a wrap. Toroidal wrapping of network visualizations supports cluster understanding tasks. This is joint work with Team Dwyer and Marriott from Monash University and Benjamin Bach from the University of Edinburgh. Traditional standard nodding representations of a network are known to produce a hairball for larger and denser networks. And thus, it makes the inspection of high-level network structures, such as clusters, difficult. One way to find better solutions to improve layer quality is to embed the network on the torus topology. This example is a simple network with a crossing. When laid out on a 3D torus, we can route the link 2 and 4 through the inner ring, and we can route the link between 3 and 5 through the outer ring. This avoids link crossing. Finally, we can slice it open and flatten it onto a 2D screen without crossing. In this work, we focus on the 2D torus representations of a network. Such torus layout diagram supports interactive panning. For example, when a user pans the diagram vertically, the network wraps around from top to bottom and vice versa. When the user pans the diagram horizontally, the network wraps around from left to right and vice versa. Note that our toroidal layout approach is different from existing pan and zone approach, which is commonly used in overview plus detailed exploration of networks. Such approach supports only panning of a zoomed area of a diagram. By contrast, our toroidal layout approach shows the entire network diagram at all times, while the network wraps around continuously when panned. One and others studied structure-aware fisheye views. They explicitly attempted to preserve high-level network structures while performing fisheye zooming. However, they did not attempt to untangle a network, nor did they conduct a perception test of network that forms a hairball structure. This example shows a community structure of 5 clusters denoted by colors. A standard force directed representation of this network leads to a circular hairball and is hard to identify its cluster structures. Chen and others presented a torus layout algorithm for smaller and simpler networks. However, their approach in our evaluation, and we found that it has limited capability to untangle a network for larger and denser networks. We propose a refined torus layout algorithm that has better node separation for larger and denser networks. We adapt the existing stress minimization layout algorithm from Chen and others to considering a more complicated torus topology. The results show that our torus diagram makes clusters more distinct and more spread out. Furthermore, we propose an algorithm that automatically pan the diagram to find a viewport that minimizes its broken links. In a real-world example, such as football networks, our torus diagram provides a better use of available space and better separation between hub nodes. For recipe networks, our torus diagram makes it easier to find their 3 main clusters in the diagram. In an online controlled user study, we recruited 32 participants comparing torus and non-torus readability for larger and denser networks. Our results indicate that for cluster identification tasks, torus diagram with automatic panning significantly outperform standard unwrapped representations in terms of error. For node cluster tasks, our results indicate that torus diagram with automatic panning significantly outperform unwrapped representation in terms of time and error. Thank you. We are happy to take any questions.